All right, so proposition 15 says, if two straight lines cut one another, they make the vertical angles equal to one another. I like this one a lot because it's another one that I think is pretty famous. Like anybody who has gone through any kind of geometry course, like in high school or something, this is a theorem that you probably came across. You were probably given, and probably it was proved to you as well. But here it is appearing in Euclid's Elements as proposition 15. So all that it's really saying, kind of in short, is that when you have two lines crossing each other, alternate angles are equal to each other. So angle CEB is equal to angle AED. Also, angle AEC is equal to angle DEB. So that's what we're going to prove. And I think it's a pretty slick proof again. So how do we prove it? Okie dokie. So we let A, B, C, D be straight lines that cut each other at the point E. Yep. All right. So I believe what we will first prove is that angle CEA is equal to angle BED. So the top and bottom angles are equal to each other. Okie dokie. So why is that true? Well, since AE is, here's kind of how I've been saying it, is stood up on line CD, we have a proposition that says the angles CEA and angle AED, the sum of those is two right angles. And that came from proposition 13. Right. But also, we have that line, not AD, it's not a line. We also have that the line DE is stood up on, and I guess I should have mentioned that CD is a straight line. I guess probably you already assumed that. But since DE is stood up on the straight line, DE is stood up on AB. It follows, by the same proposition, that angles AED plus angle DEB also equals two right angles. And this is the same proposition, 13. Well, equals are equal to equals, so common notion 1, we would have that angle CEA plus angle AED equals angle AED plus angle DEB. So that's common notion 1. And I think, again, yeah, postulate 4, just because right angles are all equal to each other. But again, I don't really think that's, I guess that should be written in there, but I think it's so obvious that I don't actually put it here. Common notion 1 is the main justification, in my opinion, for that line. Well, if that's the case, if angle CEA plus AED equals AED plus DEB, well, then both the left-hand side and the right-hand side have angle AED in common. So it follows that angle CEA equals angle DEB, and that follows from common notion 3. We can subtract off the equal angle on either side, and the remainders are equal to each other. And this is what we need. This is what we were setting out to prove. CEA equals angle DEB. So we proved that bit. And technically, when Euclid writes this out, he said he wants to do it for all of the opposing angles. So we just showed that the top and bottom angles are the same. He also in here feels that it's necessary to prove the same thing for the left and the right angles, AED and CEB, but he pretty much just says hey, you can use this exact same argument, like a symmetric argument, to show that. So I'll write that. A symmetric argument um, shows that angle CEB equals angle DEA. And I think that's a good exercise, by the way, if you're sort of new to math, if you're new to doing some of these more rigorous propositions, see if you can use this exact same argument to arrive at this conclusion. It's not going to be the exact same argument. You'll probably have to use slightly different angles, like angle sums, but it's the same idea that you're saying, hey, these two angle sums are right angles, these two angle sums are right angles. You set them equal to each other and they'll have an angle in common that you subtract off to get that CEB equals DEA. So if you want some practice, I think I think that would be a good place to practice this. Get my book off the screen there. Okay, in any case, that is what we set out to prove. So QED, therefore, etc. Following up on this, it's kind of interesting, at least in the book that I have, they have something called a Porism that comes up after this, which today we would instead call this a corollary. So corollary means like if you prove a theorem, then a corollary is something that probably should be stated as like its own standalone theorem, but it follows directly from the consequences of the previous theorem. So that's what this Porism is it's saying that, well, from this proposition 15, we also kind of get for free this other proposition, which is if two straight lines cut one another, just like we have here, then they will make, how is it stated? They will make the angles at the point let's see, it's stated they will make the angles at the point of section, which maybe that is the proper way of stating it, but I kind of feel the need to say at the point of intersection. That makes more sense to me. Seems a little bit clearer. Then they will make the angles at the point of intersection equal to, what are they equal to? 4 right angles. And this Porism, well, I guess there's a few notes to make. The first one that I'll make is that frequently with corollaries, the idea is that the proof from the previous theorem from which the corollary is derived is essentially acts as the proof for the corollary. So there's not actually a proof written in here. I want to make just like a quick kind of proof because I actually think this isn't too obvious based off of this proposition. So I'll do that. But the other thing that I kind of wanted to note is that this corollary, and this is a note that's in my book, this corollary is actually most likely not from Euclid. Like in the original elements, this corollary was most likely not there. And it was added, let me see here, it was added after the fact by, scholars of the time. But it wasn't even like hundreds of years after the fact. It seems to be based off of this note that there are so many early Greek manuscripts that had this corollary included in the elements that it's kind of like just tradition now to include this in there. But this is technically not completely historic. Euclid didn't do this, but it notes that, my book notes that it was already present in manuscripts at the time of Proclus. And Proclus was like, I believe he was more of a historian than an actual mathematician, but he was like documenting, and I think he did commentaries on like the elements and on the conics, and he lived in the 5th century of the current era. So this has been included in Euclid's elements for, 1,500 years now. So it's just kind of like a tradition to sort of keep it in there, but it's not actually in the original elements. All right, so how does this follow from the proposition? If two straight lines cut one another, they make four angles. So if we were to add up, four right angles. If we were to add up all of these four angles, it would be equal to four right angles. And this is based off of, again, since it's a corollary, this is based off of proposition 15. So proposition 15 gives us what? That CEA equals DEB. Also that CEB equals, oh, so I guess I did prove the left and right ones. For some reason I thought that I was doing the top and bottom ones, but I guess it was the left and right ones. I said that earlier in the video. Any case, nothing changes. CEB equals angle DEA. All right, so if this is the case, then we could say something like, all right, then CEA plus CEA plus CEB plus DEB plus DEA. So here's DEB, DEA. Well, all of this is equal to, if DEB is equal to CEA, then all of this is equal to CEA plus CEB plus, again, CEA plus, well, DEA is also equal to CEB. So it's like CEA plus CEB times 2. But we have, let's see, I suppose it's probably proposition 13, since that's being cited in here. Proposition 13 says that CEA plus CEB is two right angles. So this is equal to two right angles. Two rights plus two rights, which is four right angles. That's how I would go about proving that, at least. And I also feel, though, that this maybe could be like, I guess it makes sense that this is they state this as a corollary here, because I think that this could be proved just using propositions 13 and probably maybe proposition 14, but it would probably, if we only did that, if we didn't actually use so here's where we use prop 15. If we didn't actually use Prop 15, it would probably feel like sort of like we're having to put in more work into this actual proof. So it would have, rather than being a corollary, it would have had to actually be its own standalone proposition. So I feel that that's why this shows up after proposition 15 rather than after like 13, where it could have, in my opinion, I might be overlooking something or oversimplifying something, but I think Prop 13 could have proved this. In any case, there we go. We get proposition 15, and then we get another proposition for free.